recording is started. Welcome to Thursday, August 19th. You guys know that tomorrow's your quiz on just vectors of trigonometry, stuff hope it's going to be on. And also, I'm going to pick up your homework tomorrow. Okay, so you guys know quiz tomorrow, homework due tomorrow. Okay. And since the quiz is going to be on vectors, then at least get one more sharp problem on that in there. Okay. And then I'll spend the rest of the class covering the rest of these topics that are going to be pretty foundational to this class. So, what is the net force on the bananas? Hey, I got 3 monkeys all pulling on these bananas. Maybe they'll tie the vine to this bananas and they're fighting over. This guy's pulling 120 newtons straight to the left. We got 50 newtons straight down. And then we got 130 newtons at this 22.6 degree angle, 22.6 degrees. Okay. Ignore the weight of the bananas, but let's just say those are the vectors that matter. That's okay. All right, so who can tell me what is the net force on those bananas? Who knows? Yeah, Sam. Zero newtons. Oh, I should have said too, when I say net force, there's 2 parts to the answer. There's the magnitude and direction. But in this case, since the answer is just 0, then I guess the direction doesn't really matter, right? But it is a vector, so usually that would matter. Right? Did you guys all see 0? You see 0? Okay. Maybe different ways you could approach this. The analytical way would be, well, maybe I want to take this 130 Newton vector and break it into components. Say, well, how much is this monkey pulling to the right? And how much is he pulling up? Okay. Would that be 130 newtons times cosine of 22.6 degrees and 130 newtons times sine of 22.6 degrees? You guys can do that, right? Okay. What is 130 newtons times cosine of 22.6 degrees? It's 120. Hey, if this monkey is therefore effectively pulling 120 newtons to the right, he's also pulling up, but I haven't talked about that yet. 120 newtons to the right. And this monkey's pulling 120 newtons to the left. That's going to balance out along the horizontal axis, isn't it? Okay, so well, at least at this point we know the bananas aren't moving right left, right? Or I should say accelerating right left, but a few weeks from now. Okay. How about what is 130 newtons times sine of 22.6 degrees? What is that? It is exactly 50 newtons, isn't it? Yeah. And so now the bananas are being balanced out up and down, right? 50 up, 50 down, right? Right. Oh, no, that's the analytical approach that you guys want to know, sine, cosine. How many guys saw graphically that you could have these vectors tip to tail and it also zeroes out from that point of view? Here, here's what I mean. Let's say you start with 130 newtons up and to the right here. And then let me bring in this 50 Newton guy and add it tip to tail. You guys ready for this? You guys use your imagination. Pop that right in place there. Just slide the spectra up. That'll bring us down to right here. And then I'm going to bring in this guy. Slide this guy over. Guys see that? So that's 3 vectors tip to tail. And isn't the ending place of those 3 vectors exactly the origin, like starting place? They can do them in any order. You're always going to end up. Right? Like you could go, or you go. You're always going to end up at that spot, aren't you? Right? So the difference between the tail of the last guy and tip and tail, first and last guy, yeah, it's 0. It zeroes out. Okay. What kind of triangle would this be if you did that tip to tail method and made it like a triangle shape? That's a what triangle? You guys ever heard of a 5, 12, 13 triangle? It's another special right triangle. There are a few of those, 2 special triangles. Okay. So I do want to go into these last few topics. Before I do, who's got any questions about anything that might show up on the quiz tomorrow? Any questions? Questions? No? You guys good? Okay. Oh, yeah.
You obviously need to show your work with quiz, but would you need to like draw a hypothetical triangle to get the right? Like, you know what I mean?
I'm just looking for answers. If you have the right answers, then you'll be right. I create lots of different versions of the quiz, so yeah, that's really what I'm looking for. Yeah, so of course, yeah. Be able to do that, and then if you're ever ready for something for AP, then assume that the grader might want to know your work too.
For the stuff that's like the homework, are you not allowed to do the whole like 180 minus 0 minus because you said they don't add up to 100.
Oh, yeah, you can do that. So, yeah, that was a sort of trivia I was telling you about before. So when you guys are working ways around the triangles, there are multiple ways once you get the ball rolling to finish off the triangle. So one step you could possibly do is, here, give you guys an example.
But like the second one, you said that not all the time, like it's gonna, like sometimes it won't
Yeah.
happen to 180.
Yeah, guys, for a triangle, do all the angles always add up to 180 degrees? They do as long as the triangle is a flat triangle. I did give you guys a weird counter example the other day. I was saying if you're on a curved surface, that's not necessarily true. Yeah, so all our triangles are going to be flat. You could totally assume that they add up to 180 when you're doing just analytical paperwork. Right? Yeah, I guess there's sort of two different approaches to solving things in this class. There's the very textbooky, I've got paper and pen out and I'm just solving stuff. Use all your math rules for that. Flat triangles, angles always add up to 180 degrees. Right? Then there's the science aspect of this class, which is you're back in the lab, you're measuring things, and some of your measurements are just the equipment you're using, eyeballing things, using timers. There's always going to be a little bit of margin of error, and just know to look for that too. Okay, so let's say this is like 31 degrees, right angle, and this side's like 5.0 kilometers. Something crazy like that. Okay. Yeah, how could you finish this triangle off? Okay. Well, one thing you might do is say that this angle up here must be 90 degrees minus 31 degrees, which would be, is that 59 degrees, I think? Okay. But that's not the only way. You could, that's perfectly fine. You definitely do that. Alternatively, you might say, maybe I want to set up a, well, actually, you'd have to do a little bit more on this. Okay. I might find it out a roundabout way. I'll show you guys a roundabout way. Let's see, bounce off this 31-degree angle, and you want to find the opposite side. Okay. As if you know one of the legs, and you want the other leg, does that sound like sine, cosine, or tangent? Something to do with tangent, right? Let me start that tangent relationship. Tangent of 31 degrees equals, I'll call this y. What's this ratio? What over what? Exactly. Y over 5 kilometers. Can I take the 5 kilometers, cross multiply it up? 5 tan 31. Okay. So y is equal to 3 point. Whoa. I just made up the number, so I wasn't expecting this to happen. It's like 3.0 kilometers. 3.0. Interesting. Okay. 3 kilometers. And then let's say you want to use these two legs to figure out this angle. Pretend you don't know it's 59 degrees yet. Can I do an inverse tan and just do 5 over 3? Okay. Let's see what that is. What is inverse tan of 5 over 3? Inverse tan 5 on 3. Oh, it's 59 degrees. Okay. So there's two different ways to get it. So usually there's multiple ways to solve these things. Break out all your math rules and you can solve them however you want to solve them. Okay. Any other questions on trig, vectors, components? Okay. All right. So let's talk about these prefixes. Or I think at the tail end of yesterday, just talking about scientific method, prefixes. Okay. So you guys know metric system, everything's scaled by factors of 10. There's a handful of prefixes that are good to know. I'm going to list some of them here. Just be an M. Okay. There's some common prefixes. If you see, because this one's giga, got mega, kilo, milli as a prefix, got micro, and nano. Right. Obviously, those aren't all of them, but really common ones. Okay. Maybe I'll start kilo and go bigger and then work the other way later. Okay. So you guys know kilo is a factor of 1,000, which is 1,000. That's 10 to the power of what? 3. Yeah, so 10 times 10 times 10. 10 multiplied by itself 3 times. That's what 10 to the power of 3 is, right? If you guys have a computer file and it's 1,000 kilobytes, they'll bring it up to a megabyte, which is a factor of 1,000,000, which is 10 to the 6th. And then if you have a file that's 1,000 megabytes big, that can be like a factor of 1,000,000,000, which is 10 to the 9. I should say too, my example isn't maybe exactly good because computer files actually go by factors of, is it 2 to the power of 10, I think it is? Let me just double check. I think it's 2 to the power of 10. which is 1,024, which is still close to 1,000. They just borrow the prefixes, so it's actually 1,024 times it. Anyway, that aside, if we're working with like 1 kilometer would definitely be like 1,000 meters, right? 1 kilometer. How about milli? 1/1000, which is 10 to the power of what? -3. Yeah, you guys remember negative exponents just means it turns the number into a fraction. It doesn't actually make the number negative, right? You guys remember that. Okay. So for example, if I take a meter stick and I split it up into 1,000 parts, I get a tiny, tiny amount that's about that big, 1 millimeter. Micro, that's 1 billionth, 1 in a million, which is 10 to the -6. And nano is 1 in a billion, which is 10 to the -9. And smaller is like pico, right? So micro, the prefix is the Greek letter mu, which looks like a U with a tail on it. If you guys are reading like medication or supplement bottles, a lot of times there's like some number of micrograms they are, and they should let you guys know too that just for public consumption, because a lot of people don't, just in the general public don't know this, they a lot of times use MCG for microgram. Okay? In this class, we might do something more like this: microgram. So if you ever see a label that says MCG, it's really like this. Okay? Nano, you guys ever heard of like nanotechnology, nanobots? It's something order of magnitude of like a billionth of a meter. It's just so crazy small. Okay. Well, I've got this up here. You guys see this M, milli? Okay. If you saw something like this, millimeter, that's how you would read that, right? millimeter. Okay. This M, you've already seen in 3 different contexts in this class. We've got prefix milli, we got the unit meter, and what's the third context you've already seen it in? As a variable, it could be mass. So variable mass, unit meter, prefix milli. So you gotta be careful about that one, especially that letter gets passed around a lot. Next thing, scientific notation. I've sort of got scientific notation started here. You guys see 10 to the power, 10 to different powers, right? Okay. So you see what's going on with that? Hopefully that's a refresher from a math class. Okay. So let's go a little bit more down that road. Let's say you guys saw a number like this, 1.99 times 10 to the power of 30, and that could be kilograms. Okay? 10 to the 30 kilograms. Now, this is 1 kilogram. So 10 to the power of 30 kilograms. Let's you guys guess what this number is. Is this number right here, this value, is this the mass approximately of an elephant? Is this the mass of the planet Earth, or is this the mass of the sun? What do you guys think? I'll write it out while you guys are thinking. So, the expanded form. Kilograms. Good call, that's the sun. That's the sun right there. So when you get to universal gravitation, you're saying, for example, what's the gravity pull between the Earth and the sun? You might be using this number in your calculation at some point. Yeah, you guys can do that. So you want to sit here and type all these zeros into your calculator for every time you do your calculation? No. Probably lose track of the zeros, and it's really cumbersome, and you see flash of zeros across your screen. Also, are these zeros even significant? Like, do we know exactly that this is for sure a zero in this place right here? Do we know that? These zeros are effectively acting as what? Placeholders. That's all they are. They're just placeholders. Right? How much information do I actually know? I really know how much precision. Probably about that far. This is probably all I really know. Right? And then these other zeros are just acting as, you guys told me, placeholders. Okay? That's one purpose of scientific notation. Right? What if I wrote this? What if I wrote 1.990 times 10 to the 30 kilograms? Okay. Are these two numbers the same number? Or yes or no? Okay. Maybe you both have a good argument, because from a math point of view, like calculator point of view, they're treated as the same. Okay. But how is this number actually different? Yeah, it does have one more significant figure. By putting a zero there, I'm intentionally putting a zero there. I'm saying I know one more digit of precision. I know for sure that this is a zero. Right? This is another advantage of scientific notation, because if I just write out the whole number, it's like, is this is this significant or not? Well, it's kind of ambiguous. You don't really know. But scientific notation, it's like you definitely know if you know the digit or not. Do you actually have that information or not? Here I'm saying I do have the information. Here I'm saying I don't. Okay? Can you get really small with scientific notation? What if you saw this number? Just like some number of meters. Right? How many significant digits do you guys see right there? 4. Right? So here, for notes completion, 3 significant figures, 4 significant figures. Right. This is also 4 significant figures. Okay. Right. Because again, that last 0, I'm saying for sure I know that that is a 0. That's why I took the time to write it. Okay. Maybe I have some equipment where I can actually measure that. But these zeros here, now these are placeholders. They're just on the opposite side. They're just saying the decimal place parts left. Okay. So if you wrote this in terms of proper scientific notation, how would you do that? Exactly. 2.370 times 10 to the minus 5 meters. Yeah. Okay. Remember, the rule for scientific notation is, you guys have seen the pattern. You always take the decimal to a place where there's just a number in the units place. Okay? And then you adjust with powers of 10 after that. And yeah, you guys remember too that the negative exponent just means that you're dividing by 10, in this case 5 times. Okay? Divide by 10, divide by 10, just do that 5 times. Okay. Very good. What if, let's say I have a few different scales. Scales with you guys, right, that are creating some different numbers. Okay. So I've got a scale manufacturer. I've got, let's say, a scale number and a reading. Okay. Maybe I'm trying to measure this here 500 gram mass, so half a kilogram. I'll just use grams for today. I usually write kilograms in this class because that's the base unit. 500 grams, right? Okay. Maybe I have 2 different manufacturers and I get 3 scales from each of those. So scale number 1, or maybe we'll call them A, B, C, and D, E, F. I know it says number, but you guys get the idea. Okay, so I've got 6 different scales. Okay. Let's say the first 3 are measured by what's a good name for the first set of scales? How about the measurer? The measurer. And the other one's going to be, what's the other one going to be called? The knower. Yeah, the measurer and the knower. Okay, so 2 different manufactured scales. Maybe they're different kinds of scales. Maybe it's like triple beam balance and this is digital or something. Okay. So I put this here mass on each of these 6 scales. Okay. And let's say I get these numbers. So the first scale says it's 498 grams. The next scale says it's 501 grams. And third scale says 502 grams. Like that. Okay. Now I'm going to bring up the knower scales, and the readings show up more like this. I get 498.013 grams, 498.005 grams, and 498.021 grams, something like that. Okay. Now, look at this data. Which which manufacturer scales is more precise, would you say? More precise? The nowhere, right? These right here these are more precise. Right? Because they have more digits. Right? More digits is more precision. Okay? So in science class, when you say something has more precision, that means you're getting more digits. Hello, Mr. Griffin. Sorry, say it again. Oh. Right. Hold on, that name sounds familiar. First period, yeah, thanks. Let me check. No, I've never seen her, no. Yeah, thank you. All right, what are we here? All right, so more digits means more precision. Right. So I'm gonna guess that this nowhere scale is probably also more accurate. Now that maybe gets a little stickier because how do you know for sure? The only information you can ever get is by your measuring equipment. It might be your eyes or your ears, or sometimes it's certain tools that you can use. Okay? So what's like the true value? Well, that's sort of a weird philosophical question. So it's probably gonna be the nowhere scales, not the measure scale. The measure scales are definitely less precise. Assuming that these nowhere values are probably pretty close to the answer, probably more accurate. Which of the measure scales, A, B, or C, is the most accurate of those three scales? What do you guys? Definitely A, right? So this is the most accurate of the measure scales. Right? Now notice the words I'm using here. All right, so precise and accurate. Right? So in science, those specific meanings attached to those words. Right? What's precision? What's accuracy? So precision is like more digits. Looks like the nowhere has about definitely to the 10th place, and then the 100th place it's getting a little sketchy, but the 1000th place is probably just for show. Like I don't really know if it's a 3 or 5 or 1. Okay, but probably go to that 10s or 100s maybe. Okay. But accurate is like how close is it to a true value, right? And it's looking like probably the scale A is probably the most accurate of the measure values. I'm gonna draw a table for you guys. It shows the precision versus accuracy. I'm gonna do a 2x2 table, 2x2. So along one axis, we'll go with accuracy. So I'll say accurate and inaccurate. And the other scale will go precision. So precise and not precise. Okay. So accuracy, precision. We're going to do a dartboard analogy. So like a target going on for each one of these quadrants. You and your friends get together. You're going to play some darts. Okay. Play some darts. Okay. Maybe, so you can throw the darts, your friends can throw darts. Maybe you're rigging a machine. Maybe it's like a robotics competition. You can create that's dart throwing machine. So you break out your machine and it's dart, 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 dart. You're aiming for the middle and you're pretty much hitting the middle every single time. So it's accurate because it's what you're aiming for, and it's precise because it's hitting the same spot over and over again. Yes, so? Okay, so I guess I could believe that, but what are these corner situations? What would it mean to be one but not the other? Right? What does it mean to be precise but not accurate? Right? Well, that might be something like this. Dart, 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 dart. This guy's aiming for the middle. Oh, he keeps missing. But he's hitting the same spot over and over again. You know what you could probably do? You could probably just recalibrate his dart throw machine so that it is both accurate and precise, but at this point it's definitely not accurate. But it is precise. Right? What, let's bring in a third frame. Maybe he rigged up some other kind of dart throw machine. What would it be to be accurate but not precise? That might look like this. Dart, 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 dart. Right? See, they all kind of average out at the middle, right? So they don't lean like right or left or up or down. kind of average out in the middle, but it's kind of scattered all over the place. So I would say, on average, it is accurate, but definitely not precise. And then bring out your poor fourth friend and his machine. It does something like this: dart, 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 dart. So they're all over the place. Oh, this one hit the wall. Oh. So not accurate. They don't even average out to the middle, and they're not precise either because they're all scattered all over the place. Okay. Got this? Oh, poor guy. All right, I think we're ready for. Yeah, I think we're doing all right. Time. Dimensional analysis. You guys ready for a dimensional analysis review? Okay. So this is a really powerful tool. I'll show you multiple things you can do with this. You guys probably remember this from chemistry, hopefully, doing like stoichiometry kind of stuff. So we'll start with something like that, and then I'll show you guys some other cool things you can do with this. Dimensional analysis. Okay. Yeah, we'll start with the basic unit conversion, which is probably how you're used to using this tool. Okay. So how many years are equal to 1 billion seconds? So when you turn 1 billion seconds old, how old will you be? Are you already 1 billion seconds old? Is that going to happen pretty soon? It's going to happen 50 years from now? What the heck is 1 billion seconds? Okay, so I'm going to use the railroad track method. Last class I asked, some of them had seen this and some of them had never seen this. So just go ahead and follow along what I'm doing. You guys see, it looks like some railroad tracks. Okay. All right. What I'm going to do is start with my given value, which is 1 billion seconds. Right. Maybe it's too small, but okay. 1 billion seconds. Okay. Put that in the spot right here. Okay. Then, well, I want to do some conversions and eventually make my way to some number of years. Okay. So I know maybe the next step is I can convert maybe seconds to minutes. Is that okay? Okay. Now, I know that there are 60 seconds in a minute. Okay. Let's do it real fast before I get chugging along with this. How many guys have seen this railroad tracks? Railroad tracks. Who's seen this? Who has never seen this? Who's never seen railroad tracks? Okay. You have a couple guys. So I'm going to do this. I'm going to say that there are 60 seconds equivalent to 1 minute. Okay. Now, the fact that those two are equivalent, if I turn that into a fraction and I divide like that, what's anything divided by itself equal to? 1, right? So isn't this fraction equal to 1? Okay. But in terms of weird units, it's minutes per second in this case. Okay. I could also go 60 seconds divided by a minute. That's also a good 1. But the reason I write it specifically this way is because the seconds unit cancels out. And now at this point in the math problem, I would know how many minutes this is equivalent to. If I just take 1 billion divided by 60, I know how many minutes that is. Okay, so let's keep going. Aren't there 60 minutes in an hour? Should this 60 go on top or on bottom? Also bottom, yeah. 60 minutes equivalent to 1 hour. Okay. Again, because it's equivalent, I'm technically multiplying by 1. I'm not actually changing anything, but I am arranging this in such a way that minutes cancels out, and now I know how many hours it's equivalent to. Let's keep going. 24 hours in a day, right? 24 hours equivalent to 1 day. Hours. Okay. So if you stop at this point in the math problem, then say you take 1 billion and divide by 60, 60, 24, you can know how many days that's equivalent to. But I'm sure it's an enormous number of days. Let's go one more step. Okay. You guys know about 365 days per year? Let's just call it that, 365 days and 1 year. Okay. Oh, I should have asked you this with 365 go on top of bottom, but you would have said this anyway, right? The days cancels out. And at this point, I have only 1 unit left on the board. And it's exactly going to answer the question, years. Guess that? Okay. So in the calculator, I'm going to take 1 billion multiply by 1 by 1 by 1. So, okay, that's not very exciting. Then divide by all these numbers. Actually, what I'm going to do, I'm going to type it this way. Here's a billion. Actually, a billion is 10 to the 9, right? So just to be safe, I'll type it as 10 to the 9. Okay. Divide by. Okay. Then, okay, 10 to the 9. Divide by. Okay. Then I'm going to open a parenthesis. And then, it is. Yeah. Got a winner back there. Saying 31 years. Yeah. I'm going to multiply all these four, but I'm going to group them together in the denominator. So if you do that the way I'm about to do it, to make sure that you open a parenthesis after you hit the divide by, because you're communicating to the calculator that this is all grouped together. 60 by 60 by 24 by 365. Okay. That is indeed. Yeah. The number is 31.7 and the unit's years. Yeah, so when you are 31 years old, at some point in the year, you'll turn a billion seconds. I guess if you were really curious about it, you could subtract the 31 out, take 0.7, multiply by number of days, and then you could figure out like the exact day you're going to turn a billion seconds old. It would happen, and you will die. Okay, so this is probably something very similar you did in chemistry if you saw this at all. I want to show you guys some other stuff you can do with this tool that's maybe not exactly that. Okay. Let's say you're in a car, go to the gas station, fill up a tank, then you go and you drive 290 miles. Then you go back to the gas station and you spend $19.91 filling up your gas tank. And gasoline, okay, my numbers are definitely dated here. $2.19 per gallon. Yeah, from the good old days. And question I want to know is, what is your car's efficiency? What when I say efficiency, what unit do you think I'm looking for? Miles per gallon. Can you guys rearrange these numbers to somehow produce miles per gallon? Okay. This is a trick I used to use all the time too when I had a car that did not do this calculation for me. So I do this all the time. Then you can figure it out. What is that car's fuel efficiency? It's just that's fuel efficiency, right? See if you can beat me to the answer, but some of you guys have almost got it by now. I'm going to set some railroad tracks. Now, I know I want the final answer to be in terms of like miles per gallon. So I'm just going to rearrange these values so that they naturally produce that. Like the 290 miles, I'm going to pop out the numerator. 290 miles. Right? I need gallons to be in the denominator. So I like this 219 per gallon right here. I'm going to do that next. We say $2.19 per gallon, because that gives me gallons where that needs to go. Okay. That almost looks good, except that I got it too much going on in the numerator. I've got dollars, so I need to get rid of that. That's how much I spent. I spent $19.91. Okay. You see how dollars is going to cancel out? It's going to leave you with units of miles per gallon. Okay. Now, I should warn you guys that that trick right there may not work 100% of the time. For example, if there was a formula that maybe involved a factor of a half, for example, kinetic energy has a formula of 1/2 mv squared. Well, you couldn't get that factor using this method, but a lot of times this will lead you to the answer. In fact, a quick story. When I graduated, I got my degree in civil engineering, but before I was allowed to graduate, I had to take an exam called Fundamentals of Engineering. Notoriously a tough exam. Questions from all possible engineering classes, including a bunch of classes I had never taken in my life. I've seen terms and units that I've never seen. But I use this trick over and over and over on the exams. Well, if they're asking for like this quantity, which I know has this units, and they give me these numbers, I can rearrange these things and I can figure out how to multiply and divide those things. And over and over and over, I just went through the exam like that and passed it that way. So what'd you guys get?
49.
Yeah, 31.9. Is that what you guys got?
We've only got 32.
Oh yeah. If
36.2 miles per gallon, you can't really.
well,
Like you can't take better gallon, but yeah.
Yeah, I guess it matters how much precision do I have. So, like, looks like 4 digits of precision, 3 digits. It's 290. Hey, is this 0 significant? Um, yeah, so if you assume it's not, then you're right. You would have to round that to 32, and that's as accurate as you can, or I should say, as precise as you can know. 32. If you, uh,
No chemistry, they were really,
chemistry, they do care a lot.
they were really,
Okay.
they were really.
Interesting. Okay, then I should definitely let you guys know that in AP Physics, they really don't care that much. And neither do I. Okay. All right, so apparently that's good news for you guys. Right. If I throw a decimal there, you guys see a decimal? That means that the 0 now is significant. Okay. Now, you still run into a problem with what if you saw a number like 2900 and you have 3 significant digits? What's the only way you could express that? You'd have to use scientific notation, if you have 3 sig figs, like 2900. Okay. Yeah. AP doesn't really care about sig figs. I don't really care about sig figs. Your college textbook, usually how it works out is either all the numbers they give you have 3 digits, or they all have 2 digits, and then you can just get from that. However many digits they give you. Yeah. So, okay. How are we doing? 28. Okay, we're doing it. Got 9 minutes. Let's do another simple one. I'll do this one a little faster. Okay, there's 14 people going up to your party, and you want to budget how much are you going to spend for pizza? That's going to be the question. How much do I have to budget for pizza? So you start to think, well, I'm going to assume 4 slices of pizza per person, maybe average. Uh, I know that there's 8 slices of pizza, or per pizza. 8 slices per pizza. Okay. And I know it's going to be $9 per pizza. Okay. So question, how much to budget for pizza? Okay, who knows? Who knows? Yeah, Warren. $63. $63. Good call. So do it this way, say 14 people. I know there's, say, 4 slices per person. If I want the people to cancel out, I better do it this way. 4 slices per person. Okay. See, at this point in the math, people go, so if I do 14 times 4, if I stop the math right there, I would know how many total slices are being consumed. But let's keep going. 8 slices per pizza. Should the 8 go on top or bottom? Bottom. Because slices per 1 pizza, it's like an upside down fraction. Okay. But looking at it that way, the slices cancel out. At this point in the math, I know how many total pizzas to order. How many pizzas is that? Like 9 or 7 pizzas, I think. Okay. And then finally, let's go $9 per 1 pizza. So the pizza cancels out. The only unit I have left on the board is dollars. $63. Okay. Okay. You guys ready for a bit more abstract one? That one's real straightforward. All right. How about this? You have a really long arm and a string and a baseball, and you tie the string to the baseball, and you're wheeling this around your head. Come on. Is that? Oh. Got that? Yeah. Right. Let's ignore the wave baseball and let's just focus on this. Can you guys feel some tension in the string? T tension. That's holding the baseball in orbit around your head, right? Okay. Do you think that tension has something to do with the mass of the baseball? Do you think it has something to do with this radial value? Like how long the string is? Do you think it has something to do with like the radar gun speed of the ball. We'll call it V, like velocity. Or, I should really call it speed, I think, but I'll call it V anyway. Yeah. Those two things: this radial size, like this thing, the mass of the ball, and how fast it's going, like radar gun speed, just at that instant, so instantaneous speed. Okay. Right now, that's somehow related to the tension. Right. Now, you guys remember tugging on the donkey last couple of days, or bananas today? That tension is a force vector, and force is measured in newtons. Right. So force is measured in newtons, where 1 Newton is equivalent to 1 kilogram meter per second squared, right? So that looks like mass times distance divided by time squared, right? Kilogram meter per second squared, that's what 1 Newton is, right? Guys get that? Right. Question I got for you guys is, how can you multiply and divide these 3 variables to somehow get you to newtons? Okay. So you guys know that mass is measured in kilograms. You guys know that radial value could be measured in meters, and you guys know that v velocity could be measured in meters per second. Make sense? Right? And force, or tension in this case, but tension's a force, is measured in newtons, which is kilogram meter per second squared. Okay? So you can tell me how you multiply and divide these 3 variables, mass, radius, and speed, to give me a force value. Go ahead. One last thing I can't help but point out, there's 2 M's down here, completely different context. This is a variable mass, this is a unit meters. Okay, so the units can help you out there. This is like unit analysis, right? Let's see if you can get this. Somebody can get this. Somebody am multiplying and dividing these 3 guys right here to somehow give me a force unit, which would be newtons. Somehow multiplying mass, radius, and velocity to somehow get a force unit. How do you do it? Right, you figured it out. You figured it out. Keep going. How about now? Who's got it? Warren, you think you got it?
Could you just do math,
Mhm.
velocity?
Okay, you're on the right track. On the right track. It's good. It's going to be here. Force or tension is equal to. Okay, let's start putting these in place. It will be some kind of fraction. You're right. Mass is going to be somewhere up here because mass would be in kilograms, and that clips that in place, right? So kilograms is in place. What else do I need? Oh, yeah, Sam.
mv squared over r.
Oh, Sam got it. mv squared over r. mv squared over r. That's it. Okay. This is the formula for centripetal force, which we'll get to a few months from now. Okay. But let's check this in terms of units. So we got kilograms. Now v squared, that's meters per second, and that whole quantity is being squared. And then divide by radius. Radius is some number of meters. You see in green ink, I just put the units. Okay, black ink is the variables. Green ink is the units. If I expand this out, that's kilogram times meter squared divided by second squared to meters. And one of the meters cancels out. And that leaves me with kilogram meter per second squared, which is exactly what I was looking for. Okay, that'll do it. That is the formula for centripetal force. You guys get that? Yeah, so you guys know how unit analysis could probably be pretty handy in this class if you're trying to figure out how do formulas go together, how do you solve stuff. I'm going to throw last challenge question, you guys. You guys ready for a challenge question? Yeah. Why not? Sounds enthusiastic. Okay. Let's say that the energy usage of the USA is equal to 25,000 terawatt hours per year. Okay. So tera, you guys know, is 10 to the power of 12. This is watts. This is hours. Okay. Let's say that the average solar flux is 400 watts per square meter. So there's watts again, square meters. Okay. And I'll even give you max solar flux. Max solar flux is 1360 watts per square meter. And the efficiency of solar cells is 20%. Could you guys tell me how much land area would you need to meet energy demand with only solar? Now, this is a big engineering problem for lots of reasons not on the page, like how do you store energy now so you can use it later or something like that. But let's pretend that all that's taken care of and this is a pure math problem. What if you guys can figure that out? Of course, see you guys tomorrow. Have a good Thursday.